Okay, so and today we'll first talk about the six checks. And remember, we have the handout, which is pretty much you can use the handout as a cheat sheet when you work on Lab 8 and also for the final exam. So actually, the final exam, the majority of the final exam will be on regression. So you will have to do the regression analysis. It's kind of confusing because there are a lot of things you have to look at, and also basically I'm highlighting all the numbers you folks have to rate in order to conduct the six checks of your regression model, the ordinary least square. Okay, so let's begin with the first check. So actually the first check has to do with looking at the explanatory variables. So for the example, if you folks don't remember, we were using the number of 911 calls as our dependent variable, which is the y variable. And we're using a number of independent variables or the explanatory variables, looking at how the number of calls are, depending on the different factors. Can be population, can be distance to urban center, and there are some more variables for you folks to use in the lab. But here, for the example, we're going to look at three variables: population, and population of lower education. That's basically high school attainment, and also distance to urban centers. We are looking at the three X variables or the explanatory variables and using this as an example. So once again, in your lab, you can look at different variables, and also in the lab, I will be, so basically you'll be looking at least four variables, but feel free to use more if you feel like there are other relevant variables. So the first question, the first check, we're interested in whether the variables are significant. So far we have been looking at inferential statistics, and after running a regression model, really the first question we're curious about is, based on hypothesis, based on theoretical or based on empirical evidence, we know here are the list of variables that might be explaining the number of 911 calls, but do they really explain the model, or are they really significant? So for the hypothesis testing, the null hypothesis is the coefficient for the variables equals 0. So equals 0 means there's no relationship. And for the alternative hypothesis of the inferential part, we're looking at whether basically the coefficient does not equal 0. So which means the variables, they are significant, they do matter. So in this case, if we're referring to the table again, the table is actually what you will be getting after running the ordinary regression, ordinary least square regression in ArcGIS. You will be getting a report like this. There are many numbers. So essentially, by looking at the three variables and looking at the corresponding columns, you'll be getting their probability. So the p-values are reported under probability. And in this case, still we're looking at the 95% confidence level. So, by looking at the probability column for each of the variables, and also they do report for the intercept, they also report a corresponding probability and coefficient. So we can see, the probabilities are pretty small, so we can reject the null hypothesis, which means all the variables are significant. So that's just, the rough idea, but also since we're dealing with spatial data, we'll talk about another column that you have to look at, which is the robust underscore PR. So this is another relevant column we have to refer to in a particular scenario. So we'll talk about the scenario shortly. And also, generally speaking, you can just look at the probability, the p-value, to evaluate whether the variables are significant. But I do just want to mention a little bit about the mathematics, because as you folks can see, there are many other columns reported for each of the three coefficients and also the y-intercept. So in this case, you can see following the coefficient. And once again, the coefficient reports the y-intercept and also the three slope values. So the three slope values, if you write the whole equation, it's going to be, this 0.007 multiplied by the population, and then the 0.1048 times low education, and minus 0.002 times distance to urban center, and plus 19.82. So that's how you write the equation, because the coefficients are reported here. And right following the standard error, the coefficient, there's a column called the standard error. The standard error actually, it's a representation of how precisely the model estimates the coefficient. So it's, again, represents the idea of variance, variability, the standard deviation of all the different variables. And then it calculates a t-statistics. So here, actually, if you look at the three columns more closely, coefficient, standard error, and t-statistic, you'll actually see, well, it's not so clear, but I can, I can just tell you the mathematics here is the t-statistics are derived by dividing your coefficient by the standard error, and you will get your t-statistic. And if you don't, if you're not so sure, you can probably try some quick calculation on your own. Simon, do you have a question?
Can you say that again? You get your G statistic from where?
So the t-statistic is calculated by dividing the coefficient by the standard error. So, if you try to divide 19.82 by the 4.52, you will get roughly 4.38. So that's how the mathematics works. And once you have your t-statistics, the similar idea to calculating p-value. So the p-value can be derived from your t-statistic. So that's how the math works. But once again, whenever basically in our case, if we just want to really see if the variables are significant, we can refer to the p-value directly. So if you're not so comfortable about remembering the mathematics, feel free to just focus on the probability. So that's the rough idea. But also, I want to mention another scenario. So another scenario is, since we're dealing with spatial data, so there's a possibility that, like we talked about the Simpson's paradox, so which means, if you're looking at a subset of your data, the relationship can be reversed. So it's the same idea. You're looking at the whole metropolitan area of Chicago. However, maybe when you run the regression, you'll see the variables are not very significant because, like we can probably see, within the city of Chicago versus the relatively like suburban areas, sometimes the process can be very different or even opposite depending on what you are looking at. So whenever we're dealing with spatial data, and ArcGIS will report a Conquer or the BP statistic, which is the statistic we can use to help determine whether your relationship is stationary across the whole study area, which is also to say you're looking at the Conquer statistic to determine whether the coefficient or the variables may change across your study area. So for the Conquer statistic, the null hypothesis is the model is stationary. And of course, it's kind of like, it can be expressed in an equation, but here let's just, focus on how to read the numbers. And an alternative hypothesis of the Conquer statistic is the model is not stationary. So which means if we get the Conquer statistic to be, if the p-value for the Conquer test is smaller than 0.05, which actually means we can reject the null hypothesis of the model is stationary. So actually, here for the Conquer statistic, we're looking for a bigger p-value for the relationship to be stationary. I don't know if that makes sense. So it's kind of, usually whenever we're running an inferential statistics, we want to have smaller p-value because the smaller p-value usually means there are some patterns, there are some relationships. However, for the Conquer statistic, because ideally we want our model to be stationary so that we can use a single model to represent the whole scenario. So in that case, actually a small p-value is not very ideal, because small p-value means the model is not stationary. So in this case, if the model is not stationary, we have to refer to the robust probability, which is why there's also a report of the robust underscore PR. So this p-value column is to be used when your conquered statistic is significant. So let's just quickly look at our table here. So here is the conquered statistic, and also I want to emphasize that the final number, the last number within this line of the row of the conquered statistic represents the p-value. So oftentimes folks are confused about which number do I rate, because there are many numbers. The 15.94, it represents the statistic itself. However, if you're looking for the spatial, the p-value, it is the 0.001165. So once again, make sure you're reading the correct number. So for the conquered statistic, we get a p-value of 0.001, which is significant because it's smaller than 0.05. So which means in this particular case, we actually have to refer to the robust underscore PR. And again, if we are looking at the robust underscore PR, the robust p-value, all the variables are still significant. So in this case, we can actually pass our check 1. I'm not sure if there are any questions. I know we have a lot of numbers to read. So the reason why we are looking at the robust underscore PR is the conquered statistic is significant. And then, looking at the robust PR, they're all significant. So we can draw the conclusion that all the explanatory variables are significant. So we're basically we passed the check 1. So that's, well, actually, we went through a lot of calculation, but you can focus on looking at either the probability if the conquered statistic is insignificant, or the robust PR if the conquered statistic is significant. And once again, the last number within this line represents the p-value for conquered statistic. If you're not so sure, I would basically try to highlight the 0.001 if you have that option on your PDF document, so that you know which number to look at, and also highlight the robust PR. I think I should have that option. Let me highlight. Yeah. So in this case, for the first check, we passed the first check because, significant, robust PR, and they're all pretty small p-value. So we can say, yeah. So I'll just highlight it, meaning that we passed the first check. And feel free to, let me know if you are not so sure. And also, of course, we can keep talking about this when you folks start working on the lab. And then let's look at the second check. Well, the second check is looking at whether the relationships are what you expected. For example, when you run a model, in this particular case, we can try to go through things. I'll just talk about my logic just to save time, but feel free to let me know if you're thinking about the scenario differently. So looking at the volume of 911 calls, I would expect there's a positive relationship between your population and the 911 calls. Basically, more people, maybe there are more incidents. And lower education, because in the lower education neighborhood, and likely there is also a higher number of calls. And for the distance to urban center, I would assume there is a negative relationship, because closer to urban centers will likely mean there could be more traffic issues, and also, that would cause increasing number of 911 calls. And then I look at the coefficients here. Actually, we also passed check 2 because, for population, it's a positive. For lower education, it's a positive. For distance to urban center, it's a negative. So I passed my actually second check as well. So for the second check, we're basically to look at the sign of the coefficient for each explanatory variable and to see whether it is what we expected. And also, sometimes it can happen that somehow the sign is different. You're expecting a positive relationship, however, you're seeing a negative sign. So, there are many possible reasons. It could be that, there are some other factors that you didn't consider, or there are some other issues within your data or within your model. So in that case, you can actually keep going to run the other checks until, eventually you may find out some issues. It could be two variables are highly correlated, we'll talk about soon. So whenever you're seeing the check doesn't, whenever you're seeing a violation of each check, there is usually an indicator of problems, and likely you'll see problems in other checks as well. And also in terms of the interpretation, I also want to emphasize again, because in the lab, you'll be reading the coefficient. So in the coefficient, basically the slope coefficient for multiple regression, it represents, like, assuming other predictors remain constant, the coefficient would represent the unit change of the predictor, how much that would respond to the unit change of the independent variable. So in this case, if we are looking at the population, so basically that means assuming other predictors remain constant. So for, basically we can also round the number a little bit. So for each increase of 1,000 people, there will be likely 7 more (911) calls. So because I'm trying to round the number, because it's easier to rate than 0.007. So for each 1,000 people increase in terms of the population count, there will be, you can definitely just try to translate the language a little better so that you can better explain the model. The number would represent the unit change of the response variable to the predictor variable. And also to respond to Amy's question regarding the first check. So what if one of the variable is not significant? Do we not use that one? So in that case, that's a very good question. So in that case, I would still go through all the checks, because we'll go through the checks first. And then, basically, if one of the variable is insignificant, very likely you will find out other issues later on. So that will give you a clue of how do you handle. Sometimes you can get rid of the variable, or sometimes it can be an indicator of maybe you should separate your data into multiple ones, or sometimes it can be an indicator of you're missing important variables. So there could be many different reasons. So go through, like, even if your check 1 didn't meet, or your check 2 didn't go through, you still have to go through all the 6 checks in order to make your final decision on how to improve your model. So that's the second check. And also, I do want to also emphasize again on another issue. Sometimes I see people comparing directly between the 0.001 and the 0.1. However, it's not valid to be comparable in this case. So if you're trying to compare between the different explanatory variables, instead of using the coefficient, you should be using the t-statistic, because the t-statistic represents a normalized coefficient for each variable. So that is because, for example, for population measure, it measures the total count of population numbers. And for distance, in this case, it represents the distance value in feet. So, those variables are not directly comparable. So that's why the coefficient cannot be used to do the comparison directly. So if you're looking for comparing the coefficient between the different variables, use t-statistic. So basically, if you're trying to compare between population and low education and distance to urban center, you should be looking at, the four, basically, these three different numbers. Yeah, I'll just stop playing with my highlight. It doesn't do things very well. Yeah, you should be looking at the three different numbers here if you're looking to compare between the three explanatory variables. So please do keep this in mind, because I see these mistakes all the time. And also, after that, for the search check, we're looking into whether the variables are not duplicating. So basically, we're looking at whether, just to make sure there's no redundant explanatory variables, which is a very important consideration when you build a model. For example, if you build a multiple regression model, you want to make sure that each of your X variable or the explanatory variables are unique and independent. For example, if you throw in a bunch of 10 different variables, however, all the variables are kind of similar, they're basically telling the same story, then oftentimes it's going to cause a problem. So the search check is looking at the question of just to make sure there's no redundant explanatory variables. And this also points out a concept that mentioned in the book called multi-collinearity, just to make sure each of your coefficient, the explanatory variables are independent from each other. So in this case, for the search check, we're looking at the VIF number, which is the last column for each variable, each coefficient, each explanatory variable. So, this VIF number, the variance inflation factor, will help us check multi-collinearity. So it will give us an indicator of maybe some variables are redundant, and that kind of answers Amy's question earlier that, if you have a redundant variable, you should just throw out the variable and try the model again. So let me talk about the conclusion first, so that we can now just first get an idea of how to rate the numbers. So the rule of thumb is a large VIF value that is greater than 7.5 would indicate redundancy. So looking at our numbers here, they're all smaller than 7.5, which means, first of all, we passed the search check because we don't have any large VIF values for the three variables. And then we can look at the equation and quickly just to see what this means. So R squared value, I hope you folks still remember, R squared value represents, basically the model fit, or essentially the R squared value for each, because we're calculating the VIF for each explanatory variable, and to look at whether there are some relationships or correlation between the dependent variables. So essentially, the VIF is calculated by running the regression by using the interest, by running the regression on those particular target explanatory variable and using all the other explanatory variables as X variables, and you will be able to calculate an R squared value. So which means, if this particular variable is highly related to other variables or highly dependent on other variables, the R squared value will be large, because we're talking about R squared, the higher the value, the better the model. So if this R squared value is large, then that means the denominator is going to be small. And that would mean after doing the calculation for the VIF, you will be getting a large number. So that's the mathematics behind the VIF. So large R-squared value means this explanatory variable is highly dependent on all the other explanatory variables. And then if R-squared value is large, 1 minus R-squared value is going to be small. And then this whole, basically the inverse of this difference will be large. And that is why large VIF means redundancy. So large VIF usually indicates redundancy. And again, if you're not really following me with the calculation, keep in mind, whenever you see large VIF that is greater than 7.5, that means the particular variable is redundant. And you can thinking about removing that variable and try to run the model once again. So that's the third check. Again, we passed our check because we have relatively small VIF values. In the fourth check, it's looking at whether my model is properly specified. I know it's a pretty vague statement, but let's just be more specifically looking at how exactly we should be doing it. So when your model is properly specified, the model residuals, we're looking at the model residuals last time. The model residuals should be normally distributed with a mean of 0. So, last time we mentioned your residuals should be random, but also should be normally distributed. Some residuals are positive and some residuals are negative, and they should form a normal distribution with a mean of 0. So that's an ideal case. And to determine whether your residuals are normally distributed with a mean of 0, we're looking at, I guess I will just use the JB test, because I'm not entirely sure how to pronounce those. If you know, feel free to let us know, but I guess we can go with the JB test. So for the JB test, the null hypothesis is the residuals are normally distributed. And the alternative hypothesis is the residuals are not normally distributed. So the case is we're still looking at the p-value, so which means a significant JB statistic. When your p-value is less than 0.05, that would indicate that your model is biased. I know there are a lot of different numbers to rate, and that is why you will probably want to use your cheat sheet all the time, because there's no way you can remember all this, especially for now. Maybe after running the model for years, you will eventually remember, but definitely not now. Don't try to remember. Use your cheat sheet. Simon.
Okay, I remember in 416 we did this in Excel. I forgot, but can you do this in R?
We did this in ArcGIS. We're doing this again in ArcGIS. You can do this in R. I will share with my R, I will share all my R tutorials with you all. So yeah. If you're interested in learning how to do this in R, I will also share with you. Well, the tutorial will be there. Okay, so basically, coming back to the JB statistics, the fourth check, we are essentially, because we want to make sure that our model is not biased. So actually, we will be looking for an insignificant JB test. That makes sense? Because when your p-value is small, we reject the null hypothesis, which means it's going to be a problem. It's going to be biased. So again, looking at the JB statistic, and once again, only the last number represents the p-value, you can see insignificant. That's great. So which means our model is not biased. So we passed check 4. Okay, I'll just go over. Feel free to let me know if you have questions. And I think it's probably better, after going through all this and you do the homework, and we can just check back in next week, and just so that you get some practical impression of this. And also, I think I mentioned this, part of your output from the regression model in ArcGIS is you will be seeing a regression residual map, and some residuals will be positive and some residuals will be negative. That's something we went over last time. And ideally, we want the pattern to be random. And also, I think last time many of you pointed out that we need to run Moran's eye to determine. So that's our fifth check. So ideally, the model residuals should be randomly distributed across the study area. So now we're looking at spatially, the residuals should be random, some positive and some negative, but there's no clear patterns. They're just kind of scattered everywhere, and some, some concentrations, but not entirely. So it's a random distributed residual map. So in order to do this, we'll be basically running the Moran's eye, and I will be showing you the outcome shortly. So basically, if you do see some clustering of residuals, that's an indicator of missing key explanatory variables. So that's something you can keep in mind, because whenever you see a cluster of residuals, that likely means you need to look further to see maybe there are some other important explanatory variables that is missing. So again, looking for explanatory variables, that would depend on your empirical knowledge of the problem you're looking at and also the study area. But the statistics will give you a sense of maybe there are some missing variables. So whenever you're seeing a clustering of residuals, you should look for missing key explanatory variables. And to determine whether there's a clustering, we'll be running the spatial autocorrelation, the Moran's eye, the global Moran's eye. And I did for our model. Great, random. So our model had a random distribution of the model residuals, so which means we passed check 5. So that's a really ideal case so far. We have passed 5 out of the 6 checks so far, which again, it's probably not very common if you're running this for your own data, because I got this data from a tutorial from Esri. So their data are pretty well prepared and they're generally pretty good to represent the patterns. However, if you're running this on your own data, very likely you'll see the violation of many checks, and that would ask for many iterations in order to get a acceptable model. And the last check, we're almost there. Sorry for taking so long. For the 6th check, it's about how well am I explaining my dependent variable. So the last check is about actually looking at the model performance that we actually mentioned last time, looking at the model performance and the model fit. And if you still remember, basically we introduced the R-squared value, the coefficient of determination. So this R-squared value will be used to run the 6th check. However, let's come back here again. So let me just go to the conclusion first. So in order to determine your model performance, instead of looking at the multiple R-squared value, we should be reading the adjusted R-squared value. So instead of looking at this, almost like 75% of variation being explained by the model, we should be reading actually only 74% of the variation is being explained by the model. So first of all, keep in mind, you should look at the adjusted R-squared value for a multiple regression model, and then we'll talk about why. And in this case, we can see there are, 74% of variation being explained by the model. So it's, it's generally pretty good. It's not really about whether we passed the check. It's just giving us a idea of how much variation is being explained. But I will just put, I would just check 6 because we do have our answer now. So now let's talk about why we couldn't use multiple R-squared in this case. So because, this multiple R-squared value, if you do some experiments, actually, when you try to bring in more variables into your model, into your multiple regression model, whenever you're bringing one more or two more or more variables, more explanatory variables, you will see this multiple R-squared value will just keep increasing, no matter if your variable is relevant or not. So that is to say, for the multiple R-squared value, 3-variable model will always will always be better than the 2-variable model, and 4-variable model will always be better than the 3-variable model. So that's kind of not ideal, because sometimes the additional variable may be totally irrelevant. We need to normalize this problem. We need to normalize the impact of the number of variables, so that we can compare a 3-variable model with a 4-variable model without the influence of the number of variables. So the adjusted R-squared value is actually used to address this problem. So the adjusted R-squared value is a normalized R-squared value that is removing the impact of the number of explanatory variables. And once again, you can just, for check 6, you can just keep in mind that looking at the adjusted R-squared value. And also, today we're trying to, in the slides, we're trying to go through all this, the logical, the equations or the logics. However, for you to do your homework and also for you to run your model in the future, you can use the handout from last time. I will send you again. Well, I probably should have sent you earlier, but let me just send you again in case you don't have the document. Feel free to use the regression handout as a reference to go through the 6 checks and use this as a cheat sheet. Okay, so any questions for the 6 checks here? So we're doing lab 8 today, and I think I'm going to extend the lab 8 deadline. So it won't be next Wednesday. It will probably be, yeah, it will, I think I can give you until maybe the weekend of next week. So there are 2 portions in lab 8. Part 1 is about the ordinary least square regression. And for part 2, that's a new concept that we'll be covering on Monday next week. And also please remember we have a reading quiz due next week, and I will be for the new reading quiz, I will share with you a study guide, because there are some concepts. So I just want to give you a guidance on something you can pay attention to when you go through the readings. So for lab 8, part 2, you can wait until next week to work on part 2, or feel free to get started. But I think it's probably better. I just put everything together into lab 8, but I think it's, sorry, it's not April the 9th. It's actually November the 16th. Yeah. So we'll be talking about GWR next week. So you can leave part 2 to next week. I'm gonna stop recording.